Okay, hi everyone. It's 1 o'clock now, so we're going to go ahead and get started with today's lecture. So welcome back to the second lecture for CS178 Machine Learning. The focus of today's lecture is all about data. So probably by the end of today, you'll be sick of hearing me say the word data over and over again. But as I mentioned in the first lecture, machine learning is really all about how we can leverage data to help us solve very hard problems. And of course, understanding the data itself is often a key component in any kind of machine learning pipeline. And so it's really the first step that we'll do before doing any model fitting or anything beyond that. And so today we'll take a deep dive into how you can represent data, how you can explore data, and some notation that we'll use throughout the course for working with data. Okay, so just a sort of brief overview of what we'll be talking about today. We'll first discuss some various types of machine learning problems that you might encounter in the real world and also in this course. Then we'll go through some ways that you can represent and explore data using code. And then lastly, we'll have some brief details on the mathematical notation for how you can work with data in sort of this mathematical language. As I mentioned in the first lecture, this is not a mathematics course, but there is a fair bit of math that you should be comfortable with in order to really succeed here. And one of the things that can sort of trip people up when they're first starting to learn machine learning is that there's a fair bit of notation that you need to get comfortable with. So in today's lecture, we'll introduce that notation. We'll go through, somewhat quickly through it. And I will highly recommend that you guys check out these lecture slides afterwards and make sure you really nail all the notation. So before jumping into the content of today's lecture, just a couple of announcements and reminders. The first is the first homework is now available on Canvas. So check that out. Make sure you're fairly comfortable with the question that we might be asking and the sort of level of difficulty. In this homework, you should really expect to have to read the documentation for some of the Python packages we'll be using, particularly things like NumPy and Matplotlib. So you'll do a little bit of exploration of these on your own. There is, again, that tutorial I linked on the Canvas calendar, so do check that out. It's a great resource for these Python packages. And this is due Friday of next week, so you have a little over a week and a half to finish up this homework. Tomorrow there will be our first set of discussion sections on Thursday evening. The topic of these discussion sections is going to be covering Jupyter notebooks, how to use these, how to install them, as well as the basics of some Python packages you'll be using in the homeworks. So after today's lecture and tomorrow's discussion section, you guys should have all the tools you need to solve the first problem in the homework. So I recommend trying to do that pretty soon. And then after Friday's lecture, you should be able to do problem 2. And then next Monday's lecture, you should be able to do problem 3. So I don't want you guys to get the impression that you should be able to solve the homework already. But after the next few lectures, you should be able to tackle that. And again, please use the Ed discussion board for all course-related questions. There were already a few questions posted up there, which is good to see. It's good if you guys also occasionally check this, even if you don't have questions yourself. Because we'll occasionally be posting some announcements here if we have any course-related communications. And of course, please make sure that you're using the TA office hours. All the TAs for this course are great. They're very knowledgeable in machine learning. So if you have any questions ranging from homework problems to anything coming up in the lectures, even if you just want to chat about machine learning, what it's like to be a grad student working in this area, make sure you reach out to the TAs. They're all really great. One other thing I'll mention is that the lectures are recorded and the slides also will be available on Canvas. In the first lecture, there were some technical difficulties with the microphone, so sorry to all of your eardrums for that first lecture. But it seems like the lapel mic is working, so hopefully from here forward, all these lectures should be recorded for you guys. Okay, let's jump into the first section for today's lecture, which is discussing various types of machine learning problems. So, as I've said 100 times already, machine learning really is all about understanding data. Before we can really tackle a machine learning problem, it's important that we understand what types of data we have available to us. By far, the most common type of machine learning problem is called a supervised learning problem. In a supervised learning problem, your data comes in pairs, where we have some kind of x variable and an associated y variable. These x variables you can think of as inputs to the machine learning system. And the y variables you can think of as some kind of output. that we expect to come from our system. So you can visualize this as follows, where we might have some input data. A piece of sort of technical jargon here is that people in machine learning often call their input data features. So I'll be saying that word a bunch in today's lecture. We'll take this input data, put it through some kind of prediction model. We haven't quite talked about what models we'll be looking at yet, but we have some kind of predicting model. And from this model, we'll get out this output that is coming from our data set. These are often called targets. Supervised learning problems really come in two different flavors. The first are regression problems, where the outputs y that you're trying to predict are real valued numbers, i.e. some kind of scalars. So for example, y could take any real valued number. Y could also have some constraints on it, like being a positive number if you're predicting something like, say, the price of an object. It's going to be a positive number. It could also have some additional constraints, like living in some finite interval, like a comma b. It all really depends on the context of the problem that you're working on. So for a concrete example of what a supervised learning problem might look like, the x here, i.e. the inputs, the features, could represent some data we have about a house. So for example, x could contain information like the square footage of the house, the number of bedrooms in this house, where it's located, so on and so forth. Just a bunch of information. The output variables, i.e. the targets, the y variables, could then represent, say, the price of the house in dollars. And what we would like to do is somehow, based on the features of this house, predict what this house would sell for. You know, you imagine this could be useful if you're building like some kind of real estate website where you'd like to tell your customers, how much they could expect to pay for a particular house. For another example of a regression problem, the input features, x, could represent something like a weather history. So x could contain some information regarding yesterday's temperature, how much it rained yesterday, how humid it was, pressure, all these kinds of different variables. And then from this information, we might like to predict what the temperature is going to be tomorrow. And again, this is a regression problem because the temperature is just some number. It's some continuous output that we're trying to predict. In contrast to a regression problem, the other sort of major class of supervised learning tasks are classification problems. Here, the outputs are no longer sort of just continuous real value numbers, but they're instead discrete. And in this case, we'll often call our outputs, our targets, labels. In other words, our y variable now is not just taking arbitrary numbers, it's taking values in some finite set of k possible labels. So in the case of k equals 2, i.e. there's 2 possible labels we're trying to predict, this is what's called a binary classification problem. And in this case, we often let the y variable be represented as either a 0 or a 1. And we'll see some examples of this in a minute. Another piece of terminology here is that if k is greater than 2, i.e. we're trying to predict more than 2 possible labels, this is often just called a multi-class classification problem. A little bit confusingly, it's often convention that in this case, the y variables takes values from 1 to capital K, but just a bit of convention. In any case, we're just trying to predict y coming from some finite set of labels. Okay, let's look at some examples of classification problems. One classic example in machine learning is a spam prediction problem. So as our input data for our features, we might have the text of some email that you receive. And we'd like to predict from this text whether or not the email we received is a spam email. So this is an example of a binary classification problem. We have 2 labels, spam or not spam. For another example of a binary classification problem, we could be working on, say, a medical diagnostic task, where we'd like to predict whether or not a patient has a particular disease based on some information contained in their medical records. So again, this is a binary classification problem for predicting yes or no, whether or not this patient has a disease. For an example of a multi-class classification problem, you could consider taking in some kind of speech signal, i.e. like a waveform corresponding to a spoken word. And from this, we would like to classify that waveform into one of, say, 10 or 100,000 possible English words. So here, this is a multi-class classification problem. Obviously a lot harder than a binary classification problem, since we have, maybe 100,000 possible different words in the English language that we could be trying to predict. But again, this is a classification example because there's really only discrete labels we're trying to predict. It's not some continuous number as our output. Okay, our running example of a dog classifier is another example of a classification task where we might want to take in an image of a dog. So now our input data isn't some tabular data like it was in like a medical diagnostic task, but it's really an image. And from this image, we're trying to predict a label, and so it's a classification task. Here, at least according to Google, there's something like 300 breeds of dogs, so this is a pretty high-dimensional classification problem. And in fact, image classification is really quite a general problem, and trying to solve this problem has led to some of the biggest breakthroughs in modern machine learning. For example, there's this very famous data set in machine learning called the ImageNet data set. This is a huge data set. It has something like 14 million distinct images. And each of these images is coming from 1,000 distinct classes. So there's things like airplanes, cars, bikes, baguettes, pretty much anything you could imagine. And really, this is sort of a test bed for general image classification algorithms. Way back in 2010, when this data set was first released, the error rate of the best possible classifier on this data set was about 28%. So that's that first bar up in the left-hand side, which, it's not bad. 28% means about, for every 10 images our model is classifying, it gets about 3 of them wrong. But it's also not great. If you wanted to deploy an image classifier in some high-stakes scenarios, 30% error rate is definitely not good enough. One thing I'd like to point out here is that in 2012, there was really a huge drop in the error rate on this task. And this drop in error rate was powered by the advent of deep neural networks. This was one of the first real breakthroughs of deep neural networks in sort of an actual application. And nowadays, neural networks really power a lot of the exciting breakthroughs in what people are working on in machine learning nowadays. Another interesting feature of this graph here that I'll point out is that in 2015, the best performing neural network model is actually doing better than human-level performance. So if you take sort of a random human and ask them to classify images from this data set, they'll make an error about 5% of the time. And interestingly, the best neural networks nowadays only make an error about 4% of the time. So to me, that's very exciting that we can design algorithms that are better than humans at some of these perceptual tasks. Beyond supervised learning, another class of machine learning problems are called unsupervised problems. And in these problems, your data that you've gone out and collected doesn't have any targets. So it doesn't have any y variables. There's no regression task. There's no classification task we're trying to do. We really only have the features x corresponding to some kind of input data. An example of why you might actually have an unsupervised problem is if the targets that you ideally would like to predict are really expensive or time-consuming to obtain. So for example, in a medical diagnostic task, you might go out and collect a bunch of data about your patients, but actually labeling whether or not this patient has a particular disease requires going out, hiring doctors, paying them for their time, which can be prohibitively expensive, particularly for very large data sets. A typical task here, if you have an unsupervised data set, is to do something like clustering. So there might be patterns present in our data that we'd like to automatically be able to detect and pick up on. So here, just based on the visualization of some few data points, we can see that there's kind of 3 distinct clusters in our data. Now, maybe this corresponds to 3 different types of patients. Even though we don't have labels for these data points, we still might want to be able to segment them and cluster them in order to better understand the data we have available to us. And so we'll see in the second half of this quarter some techniques for doing unsupervised learning. Another type of machine learning problem that has a bit of a different flavor than the first 2 I introduced is called reinforcement learning. In reinforcement learning problems, we have an agent. In our case, it's our cute little robot friend on the left-hand side of this slide. And this robot is, say, interacting with some kind of environment over the course of time. This environment starts out in some kind of state, which we'll call S, and our agent is able to take actions to interact with this environment. After our agent takes some kind of actions and interacts with the environment, the state of the environment then changes to a new state, and the environment potentially gives us some kind of reward based on our action. The goal of our agent then is to try to maximize their reward after interacting with this environment over the course of time. So for a really good example of a reinforcement learning problem is a chess playing agent. So our agent here could be some kind of chess bot. The environment then is the state of our chessboard at any particular state in time. The actions our agent can take are then moving its chess pieces around. The environment then reacts to the actions of the agent, i.e. whoever you're playing chess against will then play their move. But I'll point out here that the rewards you get for this chess game are sparse. And by sparse, I mean you only get a reward at the very end of the game, i.e. you'll get some reward if you win the game of chess, and maybe you pay some kind of penalty if you lose the game of chess. And because these rewards are very sparse, it makes reinforcement learning actually quite a difficult task. We'll spend about a week on reinforcement learning at the end of this quarter, but if you'd like to take a deeper dive, you'll likely need to take a second course totally focused on RL. It's quite a difficult problem. Another great example of reinforcement learning in the real world and sort of what we can achieve with RL is Go playing. So if you've never played Go, it's a board game where two players play against each other. And I'd like to point out here that sort of the classical approaches in AI, things like search, logic, these kinds of things, really didn't get us very far in terms of playing Go. So all of these classical approaches are highlighted in red on the graph in the bottom right. And we can see that over time, the performance of Go playing agents really wasn't increasing all that much. That red curve is pretty flat. But really with the advent of deep learning and neural networks from about 2010 onwards, there were really huge breakthroughs in deep reinforcement learning, which eventually led to the design of a Go playing agent, which was able to beat the world champion at Go back in 2017. And so, again, I'd just like to really point out here that these data-driven approaches based on machine learning can really lead to breakthroughs that classical AI just simply couldn't achieve. Okay, so to summarize, really the sort of main focus of this course and what most machine learning problems are supervised learning problems, where you have input-output pairs provided to you during training. In regression problems, that y variable is real valued, i.e. just some kind of number that we're trying to predict. And in a classification problem, that y variable is categorical, i.e. is some kind of label. In unsupervised learning, only the x variables are provided to you during training. We don't have any y variables. And you might want to do something like clustering. And in reinforcement learning, it's a little bit different. We have some kind of agent interacting with an environment, collecting data about that environment as we go. So in this course, we'll focus on these first three types of machine learning problems: supervised, unsupervised, and RL tasks. But of course, there are different types of ML problems not falling under these headers. So you might have something like a semi-supervised problem, where only some of your data points are labeled, or something like an online problem where data is coming to you over time. We won't have much time in this course to see these other variants, but if you're interested, you can, of course, always do some reading on your own about these. Okay, so any questions on the various types of machine learning problems that we'll look at this quarter? Yeah.
Not particularly about the types of learning, but the dropping code flow, right? Is that specific to ResNet or were there other
I believe this is, yeah, I believe it's ResNet. It might be AlexNet, actually, is 2012. So, yeah. Yeah, another question. So in this course, you will mostly learn sort of the theory and the ideas behind these algorithms in the lecture. And then in the homeworks and in your projects, you'll be working with sort of practical implementations of these. So to answer your question, you'll be doing both. Yeah. Yeah, so the question is there a certain type of problem that's more popular than the others? I would say the most popular type of machine learning problem is supervised learning problems. Really, this is just kind of the most common type of data that you'll see out in the world, where you have some kind of inputs and you have the corresponding outputs and you want to learn how to map between these. Unsupervised learning is great if you have very large data sets but can't collect labels for them, but that's a little less typical than this supervised approach. And then RL is quite a bit more specialized than the other two. Okay, cool. Thanks for the questions. Now we can move on to the second part of today's lecture, which is how you actually represent and explore data primarily through code. So it's good to be familiar with what are sort of the standard computational environments for doing machine learning. Nowadays, almost all machine learning code is written in Python, and you'll be using Python in this course. Really, the sort of standard packages here are things like NumPy, Matplotlib, and SciPy, and you guys will get a chance to do some hands-on work with these. If you're interested in things like deep learning, i.e. working with neural networks, packages like TensorFlow and PyTorch are quite popular. We won't have much time to really get into the details of these packages in the class, but if you're interested, you can explore these in your projects. Some people like to reach for things like MATLAB and R, but it's mostly the statisticians who reach for these kinds of tools rather than Python. I will point out that if you guys are familiar with things like C and C++, a little bit of work in machine learning is indeed done in these languages, but it's primarily when you need to write highly performant code. So for example, if you need to write some kind of numerical linear algebra operation, something very low level, this often will be written in C++ just to get faster performance. But for the majority of code you'll be writing in machine learning, a lot of the high-level sort of ML stuff is primarily Python. And of course, there's other sort of more specialized languages for doing things like visualization, and if you're interested in maybe some type of physical modeling, there might be particular languages for that. But really, these are the main tools. I'll say a little bit more about some popular Python libraries for doing computations in machine learning. The first is NumPy, which you guys will be experts in by week 10. And in NumPy, really what this package implements is just very basic and very fast array operations. So it's kind of a lightweight package on top of the standard Python that really helps you do basic numerical computations. It also implements some very basic linear algebra, but it's mostly tools for just kind of boxing up numbers into arrays and working with those arrays. Another popular package for general purpose computation in Python is SciPy. SciPy is actually built on top of NumPy, but implements sort of higher level algorithms, such as, say, optimization, numerical integration, this kinds of stuff. Another package that you might choose to work with throughout this quarter is called Pandas. You can think of Pandas as kind of like Excel for Python. It's very useful for working with tabular data, i.e. data where you have a bunch of rows and a bunch of columns. This is also built on top of NumPy, so just illustrating that NumPy is pretty low level. And it gives you lots of nice tools for doing data manipulation, data summarization, this kinds of stuff. For plotting and visualization, which is a huge component of any machine learning project, the most common tool here really is called Matplotlib. You guys will get a short tutorial on that in tomorrow's discussion sections, and you'll use it plenty in the homeworks. But there's other packages as well, like Seaborn, which I use a little bit in these slides that you might want to familiarize yourself with. Really, all of these plotting packages are very highly flexible and allow for a very interactive data analysis. A key component in any machine learning project, if you say do some data analysis, is sharing that analysis with people who might not be technical. So for example, you might go out and work for a company, do some data analysis, and you'd like to share the insights of your analysis with maybe your manager who might not know machine learning. And plotting is really a key way of sharing that kind of information with non-technical folk. Matplotlib is really great because it's super flexible and gives you a ton of control over the plots that you'd like to create. And so it's really an indispensable tool for doing machine learning. Okay, and then next up, I'll just briefly mention a couple of basic Python libraries that are used for machine learning in particular. One that you guys will use a ton in the homeworks is called scikit-learn, aka sklearn. This is really the sort of gold standard library for doing machine learning in Python. It's open source, so you can go around and poke at the code if you'd like. You'll be using this to do a lot of your homework assignments, and it really implements most of the standard machine learning algorithms that you'll learn about in this class. As I mentioned, there's also various deep learning libraries, like TensorFlow, which is coming from Google. TensorFlow is really a broad, low-level framework for doing deep learning. It gets used quite a bit in industry and research applications. Built on top of TensorFlow is a package called Keras, also from Google. This is a bit of a more high-level API that is a little bit easier to use, a little bit more popular in sort of industry applications. And then my personal favorite here is PyTorch from Meta or Facebook. It's a more recent alternative to TensorFlow, but it's quite popular in mostly academic and research settings. And again, all these packages are open source, so I really encourage you guys to go check out the documentation, look at the code, play around with them. Okay, so now that we've seen kind of what are the various tools you might use in machine learning, let's jump into how you can explore and visualize data. So today we'll focus on exploring and visualizing supervised data in particular. A lot of what I'll say can also be applied to unsupervised data, maybe modulo some details. So it's of course very useful before you even fit a model to your data to make sure you really understand the data that you have available to you. And you can do this in various ways, such as visualizing the data, seeing what it looks like, and also doing things like, say, computing summary statistics. This first sort of basic step in a data analysis pipeline is often referred to as exploratory data analysis, or EDA. So again, we're really doing all of this before we do any machine learning. We're just trying to get a handle on what our data looks like. And the idea is we'd really like to understand maybe how the inputs X and the output Y are related. And this could maybe give us some insights on how we can build models for a problem, and also can potentially help us, say, diagnose problems with our data set. For example, if there might be some missing values. One caveat with EDA is that for very large data sets or very high dimensional data sets with lots of different inputs, EDA might be simply impractical. How do you visualize an input to a problem that has like 1,000 different variables? It's quite difficult to do. Okay, so I'd like to convince you all before looking at data visualization techniques that data visualization is actually useful. So here I have gone out and collected some data. This is actually a data set consisting of various patients who have diabetes. And what I've done is I've made a histogram of a particular variable in this data set. So in some more detail, I looked at some X variable for every one of these patients. I binned the patients based on what value of this variable they had, and then I counted how many patients fell into each bin. So again, just created a histogram of some value of these patients. And maybe let me ask you guys out in the audience, do you see anything kind of funny with this histogram? Yeah, I heard someone say it somewhere. 0, right. So there's a big spike on the left-hand side of this histogram where you have a bunch of patients who have a value of 0 for whatever this feature is. It's not necessarily problematic, but we'll see in a second that it might raise some eyebrows. Yeah?
It goes up towards 70, then plateaus, like exactly that?
Yeah, here that sort of peak might just be a feature of the fact that we have a lot of bins here, so it might be a little noisy. But really the anomaly here that you should notice is that big spike out at the left at 0. Great. So what if I told you this X variable that I'm actually plotting a histogram of is that person's blood pressure? Okay, now you should probably be thinking, okay, something's up with my data. Because apparently all of these patients in my data set have a blood pressure of 0. So unless somehow my patients with diabetes are not doing all that well, this really indicates some kind of problem in my data set. And in fact, what most likely is happening here is that all these patients who have a blood pressure of 0 recorded in this data set just had missing values for their blood pressure. You know, they went into the doctor and for whatever reason, the doctor didn't take their blood pressure. And rather than recording it as a missing value, it just got put into our data set as a blood pressure of 0. If we didn't do data visualization, if we just took this data set and stuck it into some machine learning model and tried to analyze it, you know, we could potentially get some problematic conclusions based out of this data. And so visualizing your data can be quite useful for detecting these kinds of problems. Let's look at a really concrete example of a particular data set and how we can sort of work with this data set and do some basic visualizations. So here we have a data set called the Penguin data set. It's a real small data set. It's not really a sort of real world data set. It's mostly a toy data set for illustration purposes. But in this data set, we have a total of 344 different penguins. Each of these penguins, we went out and collected 4 different real valued features about them, i.e. attributes, if you like. So for each penguin, we measured their bill length, bill depth, their flipper length, and their body mass, so how much they weighed. There's some additional attributes for every penguin here, such as the gender of the penguin, the year they were measured, what island they were found on, but let's ignore these for now. And this data set comes to us in the form of a classification problem. So each of our penguins in the data set comes from one of 3 possible classes corresponding to the species of this penguin. So we've got Adelaide penguins, chinstrap penguins, and Gen 2 penguins. If you'd like to download this data set and play around with it, there's the URL at the bottom of the slide, so feel free to do that. If we want to represent this data that we went out and collected about our penguins, really the most natural way to do so is just in a table. I.e., in this table, we'll have a total of 344 rows, 1 row for every penguin, and 4 columns, i.e. 1 column for each of the features of these penguins that we went out and collected. Since it's a classification problem, we also have those Y variables, those sort of target outputs. And so we'll have an additional column corresponding to those class labels. So if we stack all our data into a table and visualize it, this is what it looks like. Again, 1 row per penguin, 4 columns corresponding to each of our 4 features, i.e. our 4 measurements, and then another column corresponding to the class label. One thing I'll point out here is that for penguin number 339, it looks like our scientists didn't do a good job of measuring them or something like this, and we've got some nans in our data set. So here, nan stands for not a number, and really this is kind of standard notation as if you have some missing data in your data set. Here's Python code to generate that table we were just looking at. Won't go through it now, but check out the slides afterwards, and you can recreate exactly what I showed you. Beyond just sort of cracking open our data set, looking at every row, we can also compute things like summary statistics, just to get a basic sense of sort of the overall numerical information contained in our data set. So by summary statistics, I mean things like computing the mean of each particular feature. So it looks like sort of the average bill length here of our penguins is something like 43 millimeters. We can look at, say, the standard deviation of that feature. We can look at quantiles, like what's the median bill length, what's the maximum value, so on and so forth. Computing summary statistics can be quite useful for just sort of getting a handle on what values are present in our data. Sometimes it also can be useful for kind of detecting problems in our data set. Like maybe, for example, if the mean bill length was like 43 millimeters, but the max we saw like 1,000 millimeters, then okay, we've got some outliers, potentially some problems in our data. So it's a useful first step in just kind of getting a handle on the data we have available to us. In terms of visualizing our data, if we're looking at one variable at a time, a really useful tool for doing this are histograms. And I'll point out here that you have some kind of choice in how you set up histograms, right? In particular, we need to choose the number of bins we're going to use to create these. So for this first histogram here, the number of bins was chosen automatically. If I decrease the number of bins down to, say, 5 bins, I get a much coarser grained view of my data. And if I increase it up to 50 bins, I get a much finer grained view of my data. However, this introduces a lot of noise. Some of these bins here, like maybe down in the bottom left, only have 1 penguin in them. And so, you kind of need to be a bit careful here when you do data visualization, just to make sure you're appropriately representing your data. And here we're looking at, say, the body mass of the penguins, just for some context. A cool thing you can do instead of a histogram is called a density smoothing. So don't worry about the details here. It's just to illustrate another kind of plot that you can create. But what we've done is we've taken our histogram and kind of smoothed out the bins to get a smooth curve representing the distribution of this feature. If you're familiar with probability at all, this is really a probability density function of that particular variable. And the way I computed this is using something called the kernel density estimator. Again, don't worry about the details here, just know that you can create these kind of smoother visualizations of histograms. Okay, let's now look at histograms for two different features in our data set. So on the left-hand side, we've got a histogram corresponding to the body mass of our penguins. On the right-hand side, we've got a histogram corresponding to the flipper length of our penguins. And let's see, do you guys notice any particular difference in these two histograms that's kind of standing out? Yeah, there's a dip in the middle. So another way of saying this is that the feature on the left might be unimodal, it has a single peak, whereas the histogram on the right might be multimodal, it might have two distinct peaks. And in fact, this gives us some indication of what might actually be happening in our data set and might give us some insight in how we might understand this data set further. For example, if we instead plot histograms per class, i.e. per species, what I've done now is I've taken flipper length and made a histogram for all of the Adelaide penguins on the left, all the chinstrap penguins in the middle, and all the Gen 2 penguins on the right. And what you can see is that these penguins have quite different values for their flipper lengths depending on what class of penguin they are. And this might actually help explain that multimodality that we saw in the previous histogram when we kind of grouped all these penguins together. Again, Python code, please see this in the slides afterwards if you'd like to recreate these figures. Instead of looking at just one variable at a time, what we can also do is create scatter plots to compare the values of two different variables. So what I've done here is on the horizontal axis, I've got flipper length, and on the vertical axis, I've got the bill length of the penguin. And each of these dots represents a particular penguin and their corresponding flipper and bill lengths. And what you should see here is there's a pretty strong correlation between these two features, right? As the flipper length gets longer, so does the bill length. This probably shouldn't be too surprising. Bigger penguins are kind of bigger everywhere. In this version of a scatter plot, I also have the histograms plotted on the top and the right-hand side. So in the top, this is the histogram of flipper length that we saw before. It's this sort of bimodal distribution. And here we've got the histogram corresponding to the bill length. Again, Python code, check it out. One thing I'll point out here is that a lot of the plots that I've been showing today, I created using the Seaborn module. In your homeworks, you'll be using matplotlib. You can do a lot of these same things, but kind of the details will be a little bit different. So previously, when I showed you guys those scatter plots, we were just looking at two features at a time, comparing two individual inputs. But it's oftentimes useful to get a sense of the relationship between all the possible variables. So here what I've done is I've taken every possible attribute of my penguins and created a scatter plot for those attributes. So for example, in the bottom left, I'm looking at body mass versus bill length. Here I'm looking at bill depth versus body mass, so on and so forth. What you should notice is that on the diagonal of this diagram, I don't have a scatter plot. I actually just have the histograms. And this is because it's not very useful to plot a variable against itself. You just get a straight line, y equals x, basically. But again, this is a really nice way of visualizing the relationship between particular variables that you might have in your data set. Another thing we can do with scatter plots is distinguish our data points per class. So what I've done now is I'm looking at that same scatter plot that we were looking at before, except now every data point is colored based on its class label. So all the orange dots are all my chinstrap penguins, all the green dots are my Gen 2 penguins, and all the blue dots are my Adelaide penguins. And what you can see is that these classes are actually very well separated in this sort of 2D feature space. You can kind of imagine drawing a line that separates these classes very well. This is exactly what we'd like to do in a classification problem, right? We would like to look at some kind of input features and somehow separate the classes based on those. And in this class, we'll see lots of algorithmic and automatic ways that you can create these decision boundaries. Of course, in this 2D problem, you could have maybe written down the equation for this decision boundary if you stared at it hard enough. But in higher dimensional problems, we really need these algorithmic tools coming from machine learning to help us do this classification problem. But in any kind of classification problem, this is really the intuition you should keep in your mind. We have data points kind of floating around geometrically, and we'd like to somehow separate them based on some kind of decision boundaries. I'd also like to point out that sort of the way you represent your data, i.e. the features that you have in your data set, can really have a strong effect on how well you can achieve these kinds of classification problems. So we saw that in this 2D feature space, i.e. in the scatter plot, it's pretty easy to separate our classes. But if we just look at something like flipper length and look at the corresponding sort of distributions of those points, it's virtually impossible to separate out these classes. For example, how could we possibly separate all of these orange points from the blue and the green points? So my point here is that the features you have and the way you represent them matters a whole lot when it comes to classification problems. We can again look at pair plots, but also include the class labels. And what's interesting about this is that in some representations of our data, we can easily separate the classes. Maybe this one here, pretty easy to separate our classes. But here, the blue and orange points are not well separated. So trying to fit, say, a decision boundary in this sort of feature representation just isn't going to work all that well. So again, the point here is that data visualization is quite useful. It's good to really let us get a handle on the data that we're working with. It can allow us to detect problems, it can allow us to communicate information about our data set, and it can allow us to kind of derive insights about our data that might be useful later on in the modeling process. Okay. So any questions on data visualization before we jump into some notation? Yeah. Yeah, so the question is, what should you do if your data set has missing values? And there's lots of different options here, actually. The most standard thing to do is just throw away the data that has those missing values. This usually works fine, but it's maybe not ideal because you're throwing away data that you spent time and money to go out and collect. There's other techniques like data imputation, for example, where you might try and sort of fill in those values based on other data points you have in your data set. We won't have a ton of time to talk about missing data problems in this quarter. For all intents and purposes, the data that you'll work with won't have missing values. So we've kind of gone and cleaned up the data sets for you ahead of time here. Cool. Other questions on data visualization? Okay. And then for the last topic in today's lecture, we're going to introduce some mathematical notation that we'll be using throughout the rest of the quarter. So again, there is quite a bit of notation here, so bear with me. And I really recommend you guys go back and review this after the lecture. So to represent a feature vector in math, what I'm going to do is I'm going to use a bold font for a vector. So bold X represents a feature vector. And this feature vector has various components to it. So for example, x sub 2 is a component of this vector corresponding to the value of a particular feature in this feature vector. And throughout the quarter, I'll be using D to represent the dimensionality of this vector, i.e. how many total features we have in our data set. Okay, so for some concrete examples of what this might look like, if you have some information about a medical patient, for example, this feature vector X might represent all the information we have available at their patient. But the first feature in this vector might be their age. They might be, say, 21. The second feature, i.e. x2, would be their height, 6.1, hopefully feet. Their weight might be something like 200 pounds. Another example here is, say, a feature vector for a loan applicant. It might consist of some information like their age, zip code, income, and how much debt they have. So this is a particular feature vector. This is like a single data point. I'd like to point out here that you can really think of feature vectors as data points in a very geometric sense. So if we have a feature vector that has only two different features in it, we can of course plot these vectors and really think of them as sort of points in some kind of geometric space. So for two different examples, we have a red point here corresponding to maybe a feature value of 2, 3. We've also got a blue point here corresponding to feature values of 4, 1. For example, in our penguin data set, every point I was showing in these scatter plots corresponds to a particular feature vector corresponding to a particular penguin. Some comments here. Our feature vectors in machine learning are often much higher dimensional than we can actually visualize in practice. I.e., if you have, say, a 4-dimensional feature vector corresponding to 4 different inputs, you're probably going to have a hard time visualizing that as a point in 4 dimensions. But this intuition in, say, 2 dimensions is often quite useful for thinking about machine learning problems. Another thing I'd like to briefly mention is that the features that you have don't necessarily capture all of the important information about your problem. So for example, in this penguin data set, we only measured 4 numbers about these penguins. But there might have been other attributes of these penguins that we didn't measure that could also be useful for our problem. So no matter what data we have, there's also more data that we could have gone out and collected that would also be useful for our task. Okay, again, boldface X represents a single feature vector, a single data point, where, say, boldface X sub j is going to correspond to the jth component of this vector, i.e. the jth feature. But oftentimes, when we collect data, we don't collect just a single data point. We go out and collect a whole bunch of data points. And so we'll need a little bit of notation for how we work with multiple feature vectors at the same time. So let's say, for example, we went out and collected a total of n data points. We're going to introduce a new subscript here. I'll use I throughout this quarter to actually index the feature vectors. So boldface X sub I means our ith feature vector, i.e. the ith data point in our data set. Where, for example, X sub I2 is the second component, the second feature, for the ith data point, or the ith feature vector. And again, the index I here is over the total number of data points we have, here going, say, from 1 to n possible different data points. It's often convenient for us to take all of our data points, all of our feature vectors, and just stick them into a matrix, essentially just a big box of numbers containing all of our data. We'll use capital letters and a bold font for any matrices in this course. And the convention is that every row in the matrix corresponds to a single data point. So this row here maybe is our first penguin, this row here is our second penguin, so on and so forth. The other convention is that we'll have d columns, each corresponding to our particular feature. So this column, for example, might be all of the body weights of our penguins. This column here might correspond to all of the flipper lengths of our penguins, so on and so forth. And again, X sub ij is really the jth feature, i.e. the jth column, for the ith row, i.e. the ith data point. And if I use boldface X sub I really mean just the ith row, i.e. the ith data point. In supervised learning problems, we also have this vector of targets, y. I'll use a boldface y to denote a vector of targets, and I'll use y with a subscript to denote, a particular value for this regression target. And again, the convention is we have n rows for our target vectors, 1 row for every data point. So for example, we might have a very small data matrix with 2 rows, 2 patients, and 3 different features corresponding to their age, their height, and their weight. For some examples of particular elements, we might have X sub 1, 2 being the element in the first row, second column. And this is 6.1, and also X 2 sub 3, and you can check on your own that should be 145. If we instead have a binary classification problem, our target is still a vector, but rather than being real value numbers, we might have a 0